Okay, here we are, 2 o'clock. Welcome back to your favorite class. Yeah, a little thin there in the online world today. Only 7 people there. Man, must be a busy Friday, I guess. People like their computers can't turn on 'cause it's too cold, I guess. I don't know. All right, so today we're going to go over some practice problems, equilibrium practice problems. And what better place to take practice problems from than previous exams? So guess what? You get to see some previous exams today. Homework 5 is posted. It's going to be due on Wednesday. That's on 3D equilibrium and 2D equilibrium. So some of the stuff we're doing now. And your second exam for the class next Friday. I have posted practice problems on Canvas now, and I think there's 9 problems, something like that. So covering all topics, moments, couples, 2D equilibrium, 3D equilibrium. So take a look at those practice problems. I don't have the full solution up there yet, but I'll probably have that done, sometime this weekend. So I'll post my full handwritten solution sometime before the test. Maybe like 5 minutes before the test. Useful. All right. So, like I said, we're going to do practice problems today. And what better place to take practice problems from than previous exams? So here's a previous exam I gave 2 years ago in the fall. And here's a problem that I gave on my test. So here we have a vertical mast, AB, supported by a 4 kilonewton force. The top of the mast constrained by 2 fixed cables, BC and BD. So hopefully you can sort of see those there. And there's a ball and socket joint in A. We want to draw a free body diagram, determine unit vectors, and then determine the tensions in each wire. That is our charge. So we don't necessarily have to calculate forces down at our, whoa, what is up with my mouse? Down at this point. Oh man, I might need to turn this off and turn it back on. But okay, I'll let you guys copy down the problem while I sort of fix my writing pad here. Technical difficulties. Okay. I apologize if things explode suddenly. I need to try to fix this. 1 second. Okay, yeah, exploded. Okay, now we're good. Sweet, I fixed it. The old turn it off, turn it back on method always works. Give me another 30 seconds or so, copy down. Instead of like, maybe writing all these numbers here, trying to draw that in, you might just want to say where point D is in space. Might help you draw it faster. I don't know. All right. Either way, let's get to it. I'll bring the picture in here in just a second. Okay. So there we are. And really what we want to do is find T1 and T2 for equilibrium. All right. Okay, so let's do it. First thing we want to do, always for these types of problems, draw a free body diagram. And specifically in the problem, we're asked about drawing a free body diagram of this sort of vertical post here. So I'm going to draw a free body diagram of that vertical post AB. So let's go for that. So here's this vertical post, A, and up here is B. Let's put our coordinate system in here. It's just so we're hunky-dory. It's a little bit of a strange coordinate system because the y is actually sort of pointing backwards, but we'll go with the coordinate system that's actually given in the problem. So here that's x pointing backwards is y, and then sort of upwards here is your z-axis. All right. So thinking about isolating this thing, remember we kind of just like draw this outline around it, and then anytime we pass through an object, we have to cut it away according to our boundary conditions. We know for single cables, we have one single reaction force that we have to account for, generally in that direction. So I will draw those in here now. And so here we have T1, according to the image, and here we have T2. Here I've got this singular force that's kind of acting directly in the negative y direction. So let's draw that here. All right, halfway up the column. So we'll just label this directly as 4 kilonewtons. And then I got some stuff going on at A. I'm told in the problem that A is a ball and socket. And if we pull back up our notes here for 3D rigid body equilibrium, we can take a look at that chart to tell us what the forces are associated with a ball and socket. We also had a ball and socket yesterday in our practice problem. But here we are with our ball and socket again. Restricts motion in X, Y, Z, but allows rotation on all 3 axes. So here we just have limitations on the forces. And so we're just holding this in place with these 3 forces. And so we can just draw that directly in this diagram. I'll move my A out of the way for just a second. Here, this is my force at A in the Z direction. Generally drawn positive. We'll generally draw a force at A in the Y direction, positive sense. Again, I don't necessarily know that that's really the way that it's acting, but it's kind of the best method is to just assume that it's a positive direction and go with that. All right, so this is our general free body diagram. Everything accounted for. Sort of not given any information about the mass or the weight of this post, so we're just going to assume it's negligible. And we're off to the races. We're asked for T1 and T2. So that's what we're gonna be after. So that's here and here. Now I want to have a discussion again about sort of strategic selections of which equations to use, because you have 6 to choose from. Remember in our 3D equilibrium problems, you have something like sum of the forces equals 0, and your sum of the moments equals 0. And depending on sort of the situation that you have at hand, you may want to start in one set of equations or another. In this particular example, we have 3 unknown forces at one location. 1, 2, 3. So if I were to think about like doing the sum of the forces to start with, I would have to consider, all right, breaking this T2 and this T1 into X, Y, and Z directions. That's going to give me quite a few unknowns. And then all 3 of these guys here are also unknowns. So I'm going to end up with 5 unknowns if I'm going through that process. And so if I think about like just executing some of the forces straight away, I have 3 equations and 5 unknowns that are going to pop up in those equations. So maybe not a good place to start. Instead, if I start with some of the moments, which is probably a better selection, I'm going to be able to figure some things out straight away. And specifically, if I sum my moments about point A, which is this point down here, I've got those 3 unknown reaction forces, FAX, FAY, and FAZ, that are passing right through A. So we know the contribution to the moment from all 3 of those particular forces is going to be 0. And that means that when I do the sum of the moments, the unknowns, the only unknowns that are really going to rear their heads are this T1 and this T2. And since that's what I'm after in this problem, it doesn't even make sense to do some of the forces at all, okay? So we can get everything that we want just by summing the moments and setting them equal to 0. So you have to be like mindful and think about, where do I start? What's the best place to start? And how do I like minimize the amount of work? Typically, if you have like ball and socket type problems like this, it's usually the way to go because you have these 3 unknown forces that are acting at this one point. And typically when you have these ball and socket type equations or problems, it's usually best to start by summing the moments about that ball and socket joint. Okay. So all that said and done, that's really what we're gonna do here, is do this sum of the moments. But before I do that, I really need to define and figure out the rectangular components of my 2 tensions, T1 and T2. So with all that information about my equilibrium said, I still need to go through the process of defining those tensions and the components of those tensions in the various rectangular directions. All right. So first, need T1 and T2 in components of X, Y, and Z. So if we maybe thought about labeling the associated forces with those tensions, maybe we say something like the force associated with T1 is that tension multiplied by the unit vector along which that tension acts. And here in this particular problem, I'll label this unit vector lambda for tension number 1 as the unit vector that exists between B and D for tension number 1. So let's go ahead and label this unit vector here lambda BD. All right. So my T1 is unknown, and lambda BD is gotten by your unit vector fabrication between 2 points. So the way that I'm going to calculate this unit vector between B and D is thinking about what is the position vector that gets me to D from B, and then normalizing that position vector by the magnitude. Or in short, how far do I have to go in X, Y, and Z to get to D from B? Then normalizing that vector by the actual length between those two. Okay, so if I'm going from B to D, then I need to go here, 4 meters in the X, positive. In Y, since my Y is sort of pointing backwards here, I do go positive 4 meters to get from B to D. So 4 in the X, 4 in the Y. And then this point B here is located at 10 meters above the XY plane. So it's at a Z coordinate of 10 meters. And the Z coordinate of point D is at 2 meters. So to get from B to D, I have to go down 8 meters, so negative 8. So generally this will look something like 4I hat plus 4J hat minus 8K hat. All normalized by the total distance between those 2 points, which is gotten from the distance formula, the square root of the sum of the squares of the components, 4 squared plus 4 squared plus negative 8 squared. Okay, sorry about the organization here. It's a little better. Okay, so if you kind of make your way through this, whatever tension we have in that wire, it's going to be multiplied by the unit vector. It sort of acts in that direction here. 0.408 I hat plus 0.408 J hat. And then minus 0.816 K hat. Okay, so this would kind of be the unit vector directed along BD. All right, I'm going to go through the same process to define what's happening with my other tension. Let's label that as F2. Here, this is tension 2. That's the magnitude of that force. I don't know that. That's what I'm solving for in this problem. And the unit vector along which that acts. And here we're going between point B and now point C. Let's call this lambda B, C. All right. Very similar process here. I got to think about the distance between B and C and creating a unit vector between those 2 points. Okay, so here's B and here's C. I'm going from B to C. Looks like I had to go back 5 meters in X, so it'll be a negative 5X. In the Y direction, I didn't actually have to move anywhere since B and C are both in the XZ plane. My position change in Y is 0. And then my position change in Z, here I'm at 10 meters and C is sort of in the XY plane, so it'll be negative 10 meters. So quite simply, this will be, I had to go back 5 meters in I hat. I went 0 in J hat since I'm still in the XZ plane. And I also had to go down 10 meters in K hat. All normalized by the distance between those 2 points. Zero squared if you want. I'll just put it in here for completeness. Okay. And here we are. So this F2 then finally is going to be T2, whatever that tension is. And after sort of working the math here, you'll have negative 0.447 I hat plus 0 J hat if you want. Not necessary, but you can put it in there if you like, minus 0.894 K hat. And this here would sort of be your unit vector along BC. That was the unit vector before common era, lambda BC. Or is it BCE? I don't know. Okay, so now we've got these forces that are at the top of that rope in our typical rectangular coordinates. That's going to be helpful because when we start doing the sum of the moments and doing our sort of cross products, we need the rectangular components of these forces to sort of execute. All right, so now we're finally ready for our equilibrium equations, so let's do that. And as I mentioned, we're going to start with the sum of the moments equation, and really that's all we're going to need in this problem if we're just looking for the tensions. So here, now we're going to sum the moments, specifically about A equals 0. And again, the reason I'm doing this about A is because I have a number of unknown forces that travel through A. And if I take my moment about point A, those unknowns are going to disappear because the moment arm, the position vector to get to those forces is 0. All right. So let's just write out all the contributions that are going to be a part of this summation. By sort of going back to my free body diagram and taking a look at what pieces are going to contribute. All right, so if we're sitting here at A, again, none of these guys are contributing. I've sort of hammered that point home already. This 4 kilonewtons will contribute. Okay, it's not necessarily at A, so we're going to have to deal with that guy. And obviously the two tensions up here, T1 and T2, will both contribute to the moment about A, since those forces, their line of action is not passing directly through A. All right, so let's sort of write that out explicitly and show that here. Okay, so the moment at A here is going to be the position vector, which arrives at B from A. That's the top of the pole, crossed with my two forces. You could sort of do this in one of two ways. You could say that this is the resultant force that exists there, F1 plus F2. If you like that method, maybe I'll just keep them separate because we can look at each one of them separately, I think would be nice. So I'm going to keep them separate. And we can just go here, cross F1. That's the moment that's coming from sort of the cable associated with tension 1, plus a position vector that arrives at B from A, crossed with the force associated with tension 2. I've called that F2. And I have to add that last little bit, which is that sort of force that's acting in the negative y direction on my post right in the middle. And it doesn't really have a label for that point. Maybe we'd call that point C, just because it seems natural. If we call this here point C, then the last contribution here is something like the position vector that arrives at C from A crossed with that 4 kilonewton force. So let's call that the position vector that arrives at C from A crossed with, let's just call it the force at C for now. I think that's fair. So I need to make my way through each one of these guys. Well, I more or less have all of this. That's pretty easy to define. This I did already. Again, easy to define. This I did already. This guy's pretty easy, and this guy is given. So I'm ready to sort of go with all this stuff. So why don't we just take a look at each one of these separately, and then we'll just add them all up together at the end. Okay. So first here I have something like the position vector arriving at B from A, crossed with F1. Right. I haven't really stated this explicitly, but I think pretty easy to understand that if I'm trying to define the position vector of B from A, that I'm just going positive 10 in k hat. So maybe I just make that note here. Position vector arriving at B from A is 10 k hat meters. And I'll use this later. Position vector arriving at C from A is 5 k hat meters. You see this 5 here. All right. So I'm ready for my moments. And I mean, you don't have to do the full-blown kind of determinate form to calculate the moment, but maybe I'll do that here just so that we're okay. And so we'll go with F1 first, which was FBD, which is associated with T1. So here I will use I, J, K. My position vector arriving at B from A is 0, 0, 10 meters. And the force F1 is broken down into components based on that unit vector that we had, lambda BD. So here we have 0.408 T1. This is from previous, 0.408 T1. And in the K hat, negative 0.816 T1. And this here is some force vector, so it is associated with T. I guess we can use kilonewtons here. Will be the force units. Okay, we can work this out. Down and to the right. Okay, it's going to be a 0. Down and to the right. Okay, I do have some contribution here, which is going to be like 10 times 0.408 T1. Let's just go for that directly. 4.08 T1 in J hat. Down and to the right. Okay, run into another 0, so no contribution there. Let's go down and to the left. Okay, here I have an I, a 10, and a 0.408 T1. So since I'm going down and to the left, I'll have to have here a negative 4.08 T1 I hat. Continuing down into the left, okay, I run into a 0. Down into the left, I run into the 0. So no more contributions. All right, we'll continue on. Position vector arriving at B from A, cross with the force happening at 2. I, J, K. All right, my position vector arriving at B from A is the same as before, just 10 meters in K. And the force F2 we found previously, using sort of the unit vector that exists between B and C. So here this will be negative 0.497 T2. In J, 0. And K, we have 0.894 T2. Maybe let's say kilonewtons again. So again, my resulting information, nothing in I. J will have something like 10 times negative 0.497. So here we have negative 4.97 T2 in J hat. Continuing my cross product. Bunch of zeros there. Now down to the left. I 10, 0. All right, ran into a 0. J 0. Okay, so no contribution there. And here, no contribution as well. So this is all I get for that second cross product. All right, my last bit I need to consider in my moment equation is here. This RCA cross with the FC. I'll sort of restrict myself here. I don't think I really need the full-blown determinant in this situation. RCA, we showed before, is just 5 k hat meters. It's arriving at C from A. Just have to go up 5 in the Z direction. And then my force at C, if I just go back and remind myself, the force at C looks like it's 4 kilonewtons pointed in negative Y, so negative 4 J hat. All right. K cross J is generally negative I, but since I have a negative sign here, that will cancel, and I'll be left with a positive value, which here is going to be positive 20 kilonewton meters in I hat. Okay. Good thing about your shortcuts for that one too, if you don't want to actually write that, you might be able to just identify that one directly. Kind of go up here and maybe take a look. If you thought about sort of standing at A, sticking your arm in the direction of C, curling your fingers in the direction of the force, your thumb would generally be pointing in like the positive X direction. That could help you if you were thinking about shortcuts. Corelio's doing it right here in class. Don't use your left hand, okay? You'd have a bad day. Reach up toward point C, curl my fingers in the direction of the force. My thumb is in X, positive X. So here we are. Magnitude is just the multiplying those two together and in positive I. So we're ready now. Ready for some of the moments about A equals 0. Remember that this is generally 3 equations, some of the moments in X, some of the moments Y, some of the moments Z. And we're going to see from our moment equation above that we have some contributions of a couple of those different guys. Maybe we just put it all together and say that some of the moments at A from all of our contributions, something like our first guy above here, we saw 0.408 T1J minus 0.408 T1I. So I'm going to reverse that to keep I and J in sort of a standard order. Okay. Adding to that, the contribution from force number 2, which we had before, is negative 4.47 T2 in the J. Okay. So that is coming from here. Did I get that right? Sorry, I think I copied over wrong. This should not be 497, it should be 4.47. Sorry about that. That's just a hard to read my own rating issue. So it's 4.47 here. And the last little bit I need is the contribution from this RCA cross FC. So that is here, plus 20 kilonewton meters I hat. All this needs to be equal to 0 if we want to maintain our equilibrium. So again, this is 3 equations, right? 1 in I, 1 in J, and 1 in K. Unfortunately, we don't have any components in K that peek their head in, but we can still look at what's going on in the I direction and what's going on in the J direction. So let's just kind of pick one of those and go with it. I think just naturally easy just to start with the I direction. Okay. In I hat, we sort of pick all our components off. So negative 4.08 T1 and 20 kilonewton meters in I hat. And that's all we really have to concern ourselves with. So here, negative 4.08 T1 plus 20 kilonewton meters equal to 0. Well, it's convenient. We only have one unknown here. So this, if you just calculate this out, it leaves with a tension in rope number 1, just 4.9 kilonewtons. So that's nice. And finally, in J, we've got this 4.08 T1 and negative 4.47 T2. Equal to 0. Grab my T1 here. Since I've already solved for T1, I can put that in here directly. Here I know it's 4.9 kilonewtons minus 4.47 T2 is 0. Work through. This is just algebra at this point. T2, 4.47 kilonewtons. Okay, and that's it. That's all we're asked to solve for in this problem. You may be asked for like, what are the reaction forces at A? If that was also part of this problem, then you may have to do like some of the forces X, some of the forces Y, some of the forces Z to get you there. But this really is the hard bit, getting the tensions in these two guy wires. That's the hard bit. Okay, questions? Questions? Okay. All right, we have a little bit of time left. Let's maybe do a 2D problem just in the last 15 minutes here. Make sure your 2D skills are sharp as well. Okay. So this was also a question on that same exam. So this was problem number 2 on that exam. This is very similar to the previous sort of roller one that we had before. Again, the critical idea here is how do we assign the force at A given that angle of alpha? So take a look at this problem, and maybe I'll give you a minute or two to think about drawing your free body diagram and how to incorporate the reaction force at A. Okay, I'll copy the picture over and we'll get it going. Never know if when I copy and paste it, it's going to be enormous or if it's going to be like super tiny. It's never like the right size. It's just like technology. All right. So here we go. We want to find reactions at A and C. Okay. So I'm going to have to make a free body diagram here, obviously. And let's model it as just a, kind of a single L bracket. So here we are. Probably a pretty good model. All right. A. Here we are at C and B. All right. Now our free body diagram, again, I'm going to like isolate this bracket here. And so in doing that, kind of have to cut away the contribution or whatever is going on at the wall there at A. I've got to think about these 300 Newton forces that are going to be involved. And I also sort of have to cut through the pin here at C. So first thing, I'm just going to get these 300 Newton guys in there straight away. So we have 300 Newtons. We have another one here, halfway up, 300 Newtons. Okay. And now since I cut away things at C and A, I have to account for the reactions that are there. Go back to your notes for 2D equilibrium. You'll see that if we cut through a pin, we're going to have restricted motion in X and Y. So we'll have forces associated with motion in X and Y, but it's free to rotate, so no moment there. Okay. So at the pin, I'm going to have something like the force at C in the Y direction and the force at C in the X direction. Now, probably the hard bit about this equation or this particular problem is what's going on here at that boundary at A. So see, here we have a roller. And when we have a roller boundary condition, the boundary basically tells us that we cannot move through that wall. And so we have to have a force that acts to restrict that roller from moving into the wall. Otherwise, the roller is generally free to move along that direction. Okay. So the restriction that we have on this roller is that once we remove that roller, we have to account for the fact the wall can provide a force to stop that roller from moving through the wall. So that would be something that looks like this. Now the question is, when I draw that force in there, what is the angle alpha here? Is the angle alpha with the horizontal or is it with the vertical? So if I kind of think about this situation, I have to ask myself, which angle is alpha? Is this the angle of alpha or is this the angle of alpha? And how do I tell? For me personally, when I do these problems, and I kind of talked about this before, I think about drawing this with the most shallow angle of alpha possible and seeing how that affects things. If I had a roller like this, and I had a very shallow angle of alpha, shallow like my personality, and I envision just very, very shallow angle of alpha. Let's call this the angle here, alpha. All right. If I thought about restricting that roller not to move through the wall, then it'd be very obvious that my force that stopped that roller from moving through the wall would be almost vertical, but not quite. So that indicates to me that the very shallow angle of alpha would be associated with the vertical here. So in this particular problem, the force that's restricting A through the wall is associated with the angle alpha here. And we're given in the problem that this is 30 degrees. That's my method. That's how I think about it. It works for me. Maybe you have a different idea or a different strategy, but that typically works best for me. Okay. So there I am with my full free body diagram. I've got everything included now. What I'm asked for in this problem is to solve for these reaction forces that I don't know. FA, FCX, and FCY. And I know if I'm in 2D, I generally will use 2D equilibrium equations. This is in 2D. So use sum of the forces x equals 0, sum of the forces y equals 0, and sum of the moments equals 0, specifically if you want to talk about out-of-plane moments in 0, 0. These are the three equations that we have available to us for 2D rigid body equilibrium problems. All right, now where to start? Okay, you could start a couple places. You could try it a couple of ways. You want to sum the forces in the x? It's probably fine. You'd have two unknowns, the component of FA in the x direction. You want to do sum of the forces in the y? It's probably fine. You have two unknowns here. It would be FCY and the component of FA in the y direction. But I think, again, the best place to start is summing the moments about z, or summing the moments in this problem equal to 0. And that's because, again, we have two of our unknowns, FCY and FCX, both at one location. That here is point C. So if I think about summing the moments about point C in the z direction, I will really only have one unknown that appears in my equation, and that's this FA. So let's just do that. Sum of the moments about C in the z direction equals 0. I know it sounds a little strange, but that is the way. All right. So sum of the moments about point C in the z direction equal to 0. All right. I can do this in one of two ways. I can go through the full-blown idea of, my position vector arriving at this force, crossed with that force, plus the position vector arriving at this force, crossed with that force, plus the position vector arriving at this force, crossed with that force. We also know how to do that at this point. But I'm going to leverage a little bit of my shortcut methods, specifically that I know the perpendicular distance between my point of interest and the line of action of these forces. Here, the 300 newtons, and this guy, this 300 newtons. And using my right-hand rule, if I'm standing at point C, and thinking about sticking my arm in the direction of the force, curling my fingers in the direction of the force, my thumb's going to be out of the page pointed at me. So generally positive k hat. So instead of doing the full-blown cross products for these guys, I think pretty easy to understand that, for instance, this guy is going to contribute 300 newtons times 200 millimeters in the positive k hat. So let's just put those in here straight away. So starting here, my first force here, I've got 300 newtons multiplied by the perpendicular distance to get to that force. I'm going to work in meters here. It's 200 millimeters, which is 0.2 meters. And this is in k hat. I'm kind of indicating already that I'm in k hat by using the z here, so I'm going to drop the k hat generally. All right. I'm going to add to that the contribution to the moment from the other 300 Newton force, which is just below that first one. And that one is at a distance of 200 plus 200, or 400 millimeters, or if I convert to meters on the fly, it's 0.4 meters. All right, now comes the question about what's happening at A. Right. I could do my full-blown cross product for this guy if I want, but I'm lazy. I don't want to do that. If I think about the line of action of each of the individual components of this force being here and here, and I have generally those perpendicular distances to those lines of action, 800 millimeters and 400 millimeters, I can make my life easy by just saying something like the force at A is whatever the x component is, multiplied by the sine of 30 degrees, I hat, plus FAY cosine 30 j hat. Okay, so this would generally make up what is like the force A in the x direction. That's like this guy here. Totally. Okay. And also I would consider the other part of that resolved force in the x direction. Sorry, this should be the y component, and this is the x component. So now I could just think about leveraging my shortcuts, right? If I'm standing here, stick my arm in the direction of the line of action of the y direction of the force of A, curl my fingers in the direction of that force, I will have a negative general contribution to the moment from the y component of the force at A. Hopefully we understand that. Good on that? So I'm going to include that here now and say that this here is something like minus the magnitude of that force at A cosine 30 degrees. That is sort of like the y component. Multiplied by the distance that I needed to get there. Which here is 0.8 meters. All right, kind of using some advanced techniques here. Hopefully now we're sort of getting comfortable with that. I also have to think about the contribution from my x component here. Okay. That is, I'm standing here, stick my arm in the direction of the line of action of that x component of the force. So sticking my arm downwards. This is acting to the right. So curl my fingers in that general direction. My thumb will be pointing out of the page in a positive sense. So I'll have then a contribution which looks like plus the magnitude of this force at A times the sine of 30 degrees multiplied by the distance to get there is 0.4 meters. All this equal to 0. A bit heady there, but trying to maybe show some shortcuts for everybody. Only unknown here is the magnitude of the force at A. So we can just go ahead with the magnitude of the force at A, 365 newtons. The other two equilibrium equations come pretty straightforward at this point. Some of the forces in the x equals 0. We have two of those 300 Newton forces. Plus the contribution of this force in the x direction, which is going to be something like 365 newtons, the magnitude of that force, multiplied by the sine of 30, which is the contribution in the x direction of that guy, plus the reaction force C in the x direction. This is again kind of what I'm after with this equation. Those are all the components of the forces that act in x. Again, just algebra here will get us that the force at C in the x direction, negative 783 newtons. Sort of makes sense that it would be negative. It's sort of opposing all these positive values. It just means that we incorrectly assumed that it was acting to the right. I think if you just thought about this problem for a hot second, you would see that pretty obvious that the pin would have to have some force to the left to stop this thing from moving. And finally, some of the forces y and 0. It's whatever the contribution of that force at A is and the contribution from the pin at C. So here we're going to have something like the magnitude of the force at A resolved into the y direction through the cosine of 30 degrees plus the contribution at the pin at C equals 0. Here I have this already. This is 365 newtons. And so again, just algebra. Force at C in the y direction, negative 316. All right. So there you go. That'll be it for today. Kept a couple minutes extra. Hope you guys have a nice weekend, and see you on Tuesday. Work on that homework. Rawr. And don't forget to turn it in.